Good afternoon, everyone, and thank you for joining today's MaaS Insight Engage special on the Lightweight Manufacturing Centre. Thank you for taking the time today, and I've got the pleasure of presenting today with three of my colleagues, Drs. Alexander Cochrane, Dr. Sarah Bashir, and Dr. Jill Liu. So some housekeeping, please. This webinar is being recorded and will be made available on our YouTube channel. Your microphones and webcams will be turned off during the session to avoid background noise. You can type your questions throughout the session via the chat tool. Time will be allocated at the end for the speakers to answer your questions. And please use the hashtag MaaS Insights for any questions on Twitter. Please take some time to complete a survey that will be sent after the webinar. So what is the National Manufacturing Institute Scotland? So the National Manufacturing Institute Scotland is a group of industry-led manufacturing research and development facilities where research, industry and the public sector work together to transform skills, productivity and innovation to attract investment and make Scotland a global leader in advanced manufacturing. It's a One Scotland team. It's operated by the University of Strathclyde in Glasgow, and it's supported by Scottish Government, Scottish Enterprise, Highlands and Islands, High Value Manufacturing Catapult, Skills Development Scotland, Renfrewshire Council, Scottish Funding Council and South Scotland Enterprise. The MaaS group is a combination of core MaaS capabilities, specialist technical centres of which the LMC is one, and an active network of partners in the manufacturing community. The Lightweight Manufacturing Centre, as one of the specialist centres, is here specifically to provide a holistic approach to lightweighting. So that includes a number of life cycle analysis capabilities, everything from optimized design all the way through to recycling and remanufacture. So we're here today to talk about some of our testbed activities, which are really us laying a foundation for some capabilities which will help us address the net zero challenge and also help us help small to medium enterprise companies to transition into some of these new materials and manufacturing methods. A testbed in MaaS terms is an internally funded program. So this allows us to invest in both capital, so in plants, so machinery and technologies, and also in staff and research. So the LMC's testbed strategy has really been through like a three-pronged attack, which is through sustainable raw materials. So trying to move away from the unsustainable materials, which are often used in the manufacture of composite products such as carbon fibers. We're also trying to deal with the end of life of those materials and convert those into materials which we will employ in a service which we're calling manufacturing as a service. And Alex will explain a little bit more how that looks in a minute. So the LMC test beds are called Future Fibre, which is the raw material, the Reconfigurable Pilot Line, which is Alex will talk about, and composite sustainability, which Jill will talk about. So this is how they all start to work together. So this is a kind of coordinated approach through the test beds, whereby we're looking at recycled materials, sustainable virgin materials, all feeding into the Reconfigurable Pilot Line. So we're looking to partner with academia and industry to provide that translational research and technology, which will feed into manufacturing. An overview of the LMC capabilities in these fields are shown here with some of the interactions. So one of the key areas that we are developing is in materials manufacture. So we're looking to partner with academic and industrial partners to help in the material production side of the composites, which will then feed into coupons for mechanical and environmental testing, all the way through to components. And all of these are wrapped up in digital capability. So this is the value chain which we're trying to instill. So it's really, hopefully you can see the flow of these three test beds working together. And I will now hand over to my colleagues to take a deeper dive into those. The first presenter will be Dr. Alex Cochrane, and he will talk you through the reconfigurable pilot line. Alex, over to you.
Thanks, Iain. Hi, everyone. My name's Alex. I'm a research and development engineer at the Lightweight Manufacturing Centre. I'm project lead of the MaaS Reconfigurable Pilot Line Testbed programme, as Iain told you. And I'm going to talk to you a bit more about this project in some more detail and how it fits in with the rest of our programmes. So there's two themes kind of across Scotland at the moment I'd like to talk about today, and that's the target towards carbon net zero, first of all, and the provenance of SMEs is the major component of industry in the country. Both of these pose different challenges to manufacturing, and the question is, how do we balance the needs of these two things? We also face a problem in Scotland of the supply chain. So if you draw your attention to the image on the right, this is an example of composites manufacturing in particular across the UK. It comes from Composites UK, they produced this image, and it shows the distribution of composites manufacturing sites across the UK over the past few years. It gives an idea of the lack of density overall, yes, for composites specifically, but I think it can be extrapolated to all kind of advanced manufacturing activity. And what we have in Scotland is a fairly fragmented, disparate supply chain network of these types of sites. And what we need is something that's going to help with cohesion and help join up that supply chain. So to talk a little bit more about net zero, Scotland is committed to be carbon neutral by 2045, 5 years ahead of the rest of the UK, which is an incredibly ambitious target, but in many measures, it's completely living up to that task. So in 2020, though we had a lot of disruption to normal operation for obvious reasons, 97% of electricity was provided by renewables. The green energy sector in Scotland is more and more taking centre stage, and we often consider this in terms of energy production itself through, for example, wind turbine farms or tidal turbine sort of technology, marine energy technology. However, while we might produce a lot of that energy locally via renewable means, we don't necessarily have the technology here or the ownership of that technology required to do this. This raises questions of how to bring this back onshore, that ownership of technology, as the sector continues to grow. We see things like at-risk industries, so the primary one being oil and gas, which will start to contract even further as this green economy starts to build to a greater size. How can we help these industries transition to a more sustainable technology going forwards? What we want to see is an establishment of a sustainable manufacturing base that's there for the long term and it isn't going to produce more at-risk industries and is secure in its compliance with this net zero objective that's been set. Now, the flip side is that we want to pursue this target of net zero while also catering to all those SMEs that we have in Scotland. And what are the requirements of those SMEs? Those are things like flexibility and resilience in manufacturing. We've seen a requirement arise over the past year in particular of the ability to change out your manufacturing capability very rapidly. And that's been shown to be incredibly valuable and would be very valuable to SMEs operating in this kind of space. The ability to de-risk technology is really important. So SMEs will be looking to not take on major risks, which could be fatal to their business due to their scale. That's something we want to try and avoid. We also want to help them scale up and expand if they want to do that to larger production volumes. And we need to do all of this while minimizing the costs to them. On the right, I've shown a graph that comes from the EU Commission, which helps to basically illustrate what SMEs might face in terms of their journey of product development. So the green line on this graph is the risk, the blue is the costs, and the yellow is estimated profits. So along the bottom is a simplified technology readiness scale, which I'm sure many of you will be familiar with, which basically represents the maturity of the product technology as you develop it. Now, the red portion of this graph is the valley of death, which is the region where costs and risks spike, and most products under development tend to not get past this This coincides with TRL 4 to 6, which is where we're starting to take our product from that idea at the very low level of the scale. And it's been validated in laboratories and that kind of scale, but we're starting to take it to kind of small scale, what we call pilot production. So starting to try and work on the production process for that. And it's imperative that we focus on this region for SMEs. Now, a core feature of the TRL 4 to 6 region is the establishing of a pilot production line, which is basically a small scale manufacturing line used to iron out potential issues in manufacturing prior to full scale production. I've put the TRL and what we call the manufacturing readiness level scales along the top here. Manufacturing readiness level basically goes hand in hand with technology readiness level and essentially describes the maturity of the manufacturing process for your component. And for both of these scales, we're interested in the 4 to 6 region as I described. If we think of a pilot line as basically an input, so your raw material, for example, multiple cells which are performing different operations on that input, and then an output which will be our test part that we get out of that. We can illustrate the problem that we're going to face in this kind of climate that I've described if we use this sort of system by considering two separate, in this case, composite components. So in this case, I've chosen a wing spar for something like a Boeing 787 and a wind turbine blade. And I'm not going to go into detail about these manufacturing processes that I've placed here. But what I will say is that these both require very much different manufacturing overall production processes made up of different individual manufacturing processes. And if we wanted to de-risk both of these production processes, we basically have to build two completely different fixed pilot lines, which would be energy intensive. It would take up lots of space and capital, and it'd be very specific to those components that we're trying to prove out the production process for. So we believe a solution which caters to both dealing with the net zero target and the needs of SMEs that I've described is what we call the Reconfigurable Pilot Line, or RPL. So this essentially fulfills the same role as a conventional fixed pilot line, except it's formed of the basic building blocks of the reconfigurable cells, which are these grey cubes on the diagram. So this reconfigurable cell is essentially a pilot cell in which the capability can be changed out simply and quickly, and which is integrated into a larger network of cells. The network will generally be automated, where robotics are used to perform both the manufacturing processes, transport material between the cells, and measure data to relay back to a remote control center. A benefit of this arrangement is that you can retain the same manufacturing footprint while altering the capability that you have entirely, but you can also scale the manufacturing capability. So you can expand and contract that with the demand and the market conditions that you're facing. The system would be fully digitally integrated in terms of the flow of data, both between cells and back to the remote control center, allowing for a fully digital manufacturing space. And finally, our major target of this is to be accessible to the likes of SMEs. And in that sense, we're designing it to keep costs low. And we believe it's our remit to take on the risk of the development process so that that doesn't get passed on to SMEs, the risks associated with development of a system like this. So as I've described, the building block of this RPL is the reconfigurable cell. This is an example here of what that reconfigurable cell might look like. And for this example, I've used our proof of concept cell configuration for which design is actually completed and we'll be building over the next 6 months. A smart workbench, which is this thing here, this table, forms the basis of the cell. And this is an entirely proprietary design that I'll describe in detail in the next slide. But it forms the work surface upon which the manufacturing process can be hosted. It's 2 by 2 meters by about 0.85 meters in height, and its height can be adjusted. This will all be plugged into the workshop services via a monoblock connector for data, electricity, air, and water. Believe it or not, all in one connector, and that connector is integrated into the table itself. The industrial robot that I've shown here is specific to this initial cell, and in this case is going to be performing automated fiber placement for us via an end effector that will attach to it. And that's going to be our kind of proof of concept manufacturing process. However, we do plan to retool this robot to perform different operations on the same cell at a later stage. The supporting robotic elements that I've shown here are cobots and an automated guided vehicle, or AGV, and those are there for material handling and transport of material between cells. The idea is that this initial cell will prove the concept of the reconfigurable cell and show that it works, and then we can then start to scale up to multiple cells. So just to go into a bit more detail on the workbench, so the kind of smart workbench is the backbone of this reconfigurable cell. It's constructed from machined aluminium plates using standard fasteners for easy assembly and disassembly. And the design aims to focus on ease of assembly and transportation. So the metallic plates can be easily stacked and located on each other using inbuilt location features that we've designed. And the lifting of the plates can either be done individually or as groups or even the entire table at once, depending on the lifting capability available. But it has been spec'd so that the weights are kept reasonably low so that lifting shouldn't be a problem. Multiple channels are built into the cell, which allow for routing of cabling, as you can see here, and for things like operators to reach inside if need be. And spacers are included. So these smaller plates are spacers, and there's some more in the top surfaces here, for height adjustment. So those can be added or removed for height adjustment of the cell within reasonable limits. The entire system sits on a high-spec adjustable feet, which basically allow for leveling of the working surface and also provide vibration isolation capability. And the T-slot table on the top is basically designed to provide a flexible work surface, which basically can host any manufacturing capability and provide rapid installation and removal. This capability is to be provided with service connection via the table itself. So whatever manufacturing capability is on top will be plugged in to the table. And it's all designed to be it's installed and reconfigured in a single shift. That's one of our major focuses, is how rapidly we can get this in and out. The workbench is currently being mocked up in plywood in our workshop, and we will have a full mock-up available if anyone is interested in seeing that in our workshop within the next 6 to 8 weeks. We then want to expand our single cell capability. Once we've proven that first cell, we want to expand into a reconfigurable line where we have 2+ cells which host different manufacturing processes but form the same overall pilot production line. This essentially would start to provide the reconfigurable aspect of the line itself, where we could demonstrate that you can slot in and out capability as required. We could show that material can be transported between cells automatically and handled by the cobots and between the cells and areas around them like buffer zones. Cells would be digitally embedded in the workshop and in the network. And in this sense, we'd want to feed our measured data from those cells back to a central control room where we would have a virtual line represented. And this is our real gold standard for this project, is establishing a digital twin of our reconfigurable line where it's operated or viewed remotely from a remote control center. And this is the real target here. And we envision to have that established within the next 2 years. So just to summarize, overall, we have real confidence that this solution can help to improve Scotland's manufacturing ecosystem based on both complying with net zero targets and helping SMEs to survive and ultimately thrive. If you're interested in the project, for example, if you're looking to partner with us in the future and host your technology on one of these cells, or perhaps you're looking to actually help us develop the technology, or even you're looking to be an end user of this technology, you're looking to de-risk something and actually make use of the benefits that I've described, we would love to hear from you. My contact details are here on this slide and will be provided at the end of the presentations. If you'd like to ask any questions, I'd love to answer them at the Q&A session at the end of the webinar, but please feel free to add any questions to the Q&A box now and throughout the next presentations. That's all I've got to say, so thank you very much for listening, and I'll pass on to the next presenter. Thank you.
Okay, can you see my slides okay?
Yes, that's fine.
Okay, so hello everyone, I'm Saira Bashir, and today I'm going to talk about one of the other projects that we have running at the LMC called Future Fibre. So before I go into what Future Fibre is about, I thought I'd give a bit more background on how some of various types of fibers are formed, in particular carbon fibers. Those are the types of fibers that we're interested in for our project. carbon fibers, they're used as reinforcement materials in composites. And the advantages of carbon fibers are that they are lightweight and they possess very good mechanical properties. The carbon fiber reinforced composites are used in a variety of applications. For example, they're used to make structural components in automotives and also aircraft. The carbon fibers, they're produced from fossil fuel. So the fossil fuel goes through a series of chemical processing steps, and then you get the acrylonitrile, which is then polymerized to form polyacrylonitrile, or PAN for short. And then the PAN is spun into fibers, and these fibers go through a series of thermal processing steps. It's usually at a very high temperature, up to around 1000 degrees or above, that these fibers are heated to, and that burns off most of the non-carbon atoms. So at the end, you're essentially left with the carbon fibers. There are a range of issues associated with the industrial production of carbon fibers. One of the main issues is to do with the resource that's used to make them, which is fossil fuel. We all know that fossil fuel is a finite resource and it's not very environmentally friendly. If we look at the industrial process of carbon fibers, it involves a series of thermal processing steps and stretching processes, and it's a very complex and expensive procedure. And as a result, the carbon fibers at the end, they would be very expensive to buy and use in applications. If we compare it to other materials that are used for similar applications, for example, steel, carbon fibers can be up to 10 times more expensive than steel. So what we want to look at is alternative resources to fossil fuel for making carbon fibers. And this ties in with the net zero theme that has been carried forward in these presentations. So we want to find a more eco-friendly way of making these carbon fibers. If we look at the literature, one of the main resources that's used currently to make carbon fibers, as opposed to fossil fuel, is wood biomass. So the wood biomass, it contains certain components that can be processed to make carbon fiber. One of the components is lignin, so that can be spun into fibers, and then the lignin fibers can then be heated to a high temperature or carbonized. That's the procedure that is called, to form carbon fiber at the end. There's another component in biomass called cellulose, and that can go through a series of chemical processing steps to get the acrylonitrile and then the PAN. We all know that PAN is one of the key industrial precursors for carbon fiber, and we can potentially make PAN from cellulose in biomass. So there's been a range of studies published already in this area, but one of the major drawbacks with these biomass-based fibers is the mechanical properties. So if we look at top of the range carbon fibers that are industrially made from PAN, they can reach as high as 7 gigapascal, which is a very high tensile strength. But if we look at the strength of the fibers in the literature from the biomass as the resource, the strength of these fibers tends to be around 1 gigapascal. So there is a very huge difference between the mechanical properties that can be achieved with these two types of fibers. And currently that's one of the main limitations of biomass-based fiber. And that's where the Future Fibre project at LMC comes in. So essentially we are a hub that's looking to develop fibers from sustainable resources such as wood biomass. And we want to be able to make these fibers for industrial applications. It's going to be a highly collaborative project. So we're looking to collaborate with academics and also people from industry as well. So, with the Future Fibre, we are going to provide the environment, the infrastructure, the resources to exploit any research opportunities. So if you have anything in mind with regards to projects, So if you want to make certain types of fibers, but maybe you don't have the resources or infrastructure to achieve that, you can come to us and we can provide that for you, and we can collaborate and submit bids to funding councils such as EPSRC and UKRI, or it could be a core directly funded research project. I was talking about carbon fiber quite a bit in this presentation, and that's going to be one of the main research focuses for us, to develop sustainable carbon fibers, but also that are of a high mechanical property so that they can be used in industrial applications. With Future Fibre, our scope is very broad. So we're not only going to look at carbon fibers, we plan to look at thermoplastic fibers and films as well. So here is just a diagram that shows how the Future Fibre is, how it ties in with the other LMC projects. So the fiber is essentially at the very beginning of the cycle. So we plan to produce the fibers, in this case from sustainable resources, and then we want to be able to process them to make composite components. And that's where the Reconfigurable Pilot Line project could help us out with. And then once these composite components are made, eventually we want to be able to optimize them and scale up the production of the composites and ultimately be able to use them in industrial applications. We all know that composites, when they reach the end of their life cycle, they are usually just thrown away in landfill. We don't really recycle fibers from these composites, but here we want to look at net zero. We want to have a closed loop system where we're not throwing anything away. We're making use of the materials that we have, and we're avoiding fossil fuel. And in this case, we want to reuse the composites that reach the end of their life cycle and reclaim the fibers and feed them into this cycle again. And that comes under the Sustainable Composites project at LMC, which Jill will talk about later on today. So the Future Fibre program is made up of various stages, and we're initially in the first stage of setting up a lab scale fiber production facility at LMC. So the plan is to produce the fibers at a small scale and optimize the formulations and the properties of the fibers. Then the next stage would be to process the fibers to make small scale composite test specimens or coupons. And once we've achieved that, the next stage naturally would be to scale up the fiber production to pilot scale. And by that stage, we should be able to produce significant composite specimens, which ultimately can then be used as components in industrial applications. So our lab scale production line is almost complete. There's one bit of equipment that we're looking to purchase this year to complete the production line, and that's the most critical equipment, which is the fiber spinner. So the fiber spinner essentially is what will produce the fibers. So you can make fibers from a melt or from a solution. We're going to look at mostly melt spinning of the fibers. Right now we're looking at different suppliers, and there's certain fiber spinning systems that can produce fibers from melt spinning, and it can achieve that at a very small scale. And that would be ideal for us because we're in the very early stages of fiber formulation development, and that would also be useful for potential clients. So if you're looking to produce a type of fiber, but you don't want to produce a huge quantity, you might want to produce a small amount just to do some screening tests, then this sort of equipment would be ideal for that. And there is one equipment that is very modular in design, so it can be used to make not only fibers, but also films as well. So that's all from me. Thank you for listening to the presentation, and I'll hand over to Jill, who will talk about sustainable composites, and will address any questions that you have later on today. So you can post any questions you have in the Q&A section. So thank you.
everyone. Hope you can see my screen now. So yeah. So my name is Jill. I'm a composite engineer at the Lightweight Manufacturing Center, and I'm leading the sustainability related research activities. And today I'm going to talk about the sustainable composites, which is another important ongoing program at the Lightweight Manufacturing Center. I think at the very beginning, let's just refresh our motivations to use the composite material. I think one of the shining points maybe you can think about is solving the CO2 challenge. We all know there's some legislations, but the detailed numbers are here. So by 2021, which is this year, all the automotive manufacturers, they need to make sure the fuel consumptions of all new cars need to be below 95 grams CO2 per kilometer. And if you can't make it, penalty will be applied. So if we look at the tables at the right-hand side, which listed some CO2 numbers for lots of popular automotive manufacturers, so we probably can say there may be only just 4 of them can meet the target, and which are shown in green color. So if we can do some simple calculations, we can easily work out how much the penalties will be for them individually. So I think that's one of the reasons currently all the car makers are keen to explore the electrical vehicles. So I think there are probably 3 main solutions for this CO2 challenge. The first one can be like increasing the powertrain efficiency, and then the next one can be the alternative fuel approaches, like electricity, or in the future can be hydrogen. But this webinar is more about materials and manufacturing, so we more talk about the lightweighting. If we think about lightweighting, I think the material selection is the key thing. So let's look at the figure at the bottom, which indicating the tensile strength per unit density, which means the specific mechanical performance for different material. So you can see carbon fiber is excellent compared to the other traditional materials like steel or aluminum alloy. So, but we not just talk about the mechanical performance, we also think about the energy costing and the CO2 emissions to the raw materials. So if you manufacturing virgin carbon fiber, it's going to cost 5 to 6 times higher energy compared to manufacturing the steel. And it is only a little bit less than the mechanism. But raw material cannot represent everything. We need to think about the component and the parts. We do that in manufacturing because of mass saving. So actually you use less carbon fiber to match the same mechanical performance compared to the other materials, which generate less CO2 emissions compared to aluminum alloy. So which means like carbon fiber is a good candidate for now. So let's move on to the next page about a little bit detailed brief case study. So if we can make a car 30% lighter, use carbon fiber, then we can save 50 tons of CO2 per 1 ton of carbon fiber used in 10 years life cycle. And similarly, for the aerospace sectors, if we can make the aircraft 20% lighter using carbon fiber, then we can save 1,400 tons of CO2 under the same condition. I think the conclusion is very clear that carbon fiber shows a very significant negative environmental impact. So I think that's why you can look at the bar chart at the top. The market size of composite material is keep growing. And when it becomes more and more popular, we need to think about the recyclability of this kind of material, because we do have some other legislations for recycling and reuse. So at least 95% of the new vehicles by weight need to be recycled, and 85% of the waste should be reused since 2015. So let's go through some detailed numbers to make you have clear understanding of how important it is to solve this problem. So after some life cycle analysis and some case study works, we can, based on the data, we can say like by 2035, even just talk about aircraft sectors, we're going to receive 23,000 tons per year of end-of-life waste, carbon fiber waste. And on the other hand, let's look at the wind turbines, which manufactured by the glass fiber composites. So by 2030, we're going to receive 100 tons per year waste from wind turbines. And you can have a look at the chart at the top, which shows there's the waste generated from the wind turbines in UK. And there's a sharp increasing after 2028, which means the very initial generations wind turbines facing retirement. And we definitely want to need and have to find the proper solution for them. What is the current status for this material? So there's only 20% of carbon and 30% of glass fiber waste go through recycling, and a large number of this kind of waste just go to landfilling. And recycling doesn't mean properly reused, because if you not convert that to much valuable material, recycling can be generate another round of waste. Because you can see the number here, only tiny, like 2% of recycled carbon fiber and 6% of recycled glass fiber currently being properly used. So now we understand what's the issues and how important we invest our efforts in this area. So what are the current technologies we can think about and we can use? So here I summarize the different technologies about the recycling of the composite material. So if we would like to reclaim the material and use that as much as possible, so we maybe need to focus on the thermal process currently. So I highlighted 3 technologies from those. So the first one is pyrolysis, which has already been commercially used. And the second one is the fluidized bed, which can be scaled up to the pilot scale. And it can generate much cleaner fibers compared to the fibers from pyrolysis. And the pyrolysis is kind of like lab scale rigs. I won't describe too much details about this. So every time we talk about recycling technology, people always asking about the energy cost. So then I came up with this graph here, so we can compare the energy cost to make virgin carbon fibers and also the energy cost for different kind of recycling technologies. You can see the pyrolysis, which is widely used, it only costs 20% of energy compared to the virgin carbon fiber manufacturing. And if you take it in mind and in your calculation, you can easily work out the CO2 emissions. Actually, recycled carbon fibers CO2 emissions is significantly lower compared to the virgin carbon fiber, and even lower than aluminum materials. So then we can come up with the solutions, like carbon fiber is the good candidate for lightweighting and net zero, and recycled carbon fiber can behave even better. So then let's look at the current recycled carbon fiber product available on the market and in the research area. So maybe this is the first time you have looked at the recycled carbon fiber. Actually, the format is really fluffy and 3D random. It's very different compared to the virgin fiber format. So we need to definitely have some reprocessing technologies to convert this kind of material to much valuable and widely used material. So the easiest way is convert that to milled powder and some kind of pellets, which has been already widely used in construction material. And the second group, we can convert that with some traditional textile technologies to make some non-wovens and, for example, 3D preform. But because the fiber orientation here is all still random, fiber orientation is one of the dominating factors for mechanical performance of composite material. So you want to achieve very high performance with this non-woven and 3D preform. Then research developed another like group of materials. So you can, for example, the hybrid yarns, you can achieve a continuous material format and easily adapt within the braiding and weaving technologies to make recycled fiber fabric, but the question is, you're going to invest more money and energy in the weaving and braiding technologies. So in the end, like the researchers from the University of Nottingham and University of Bristol, they developed aligned fiber tape and tows, which make the recycled material looks very similar to the virgin fibers and improve the mechanical performance and make it valuable and available to volume manufacturing. So what we can do from the Sustainable Composites program and how we're going to achieve that, we're going to collaborate with academics and the RTOs and to generate some innovative ideas and do the knowledge exchange and to collaborate with the industrial partners, and of course we feedback to and collaborate with government bodies to make sure we're monitoring and collect the data to summarize the society, environment, and economic impact from our program. So what kind of service and product we can provide? We can provide the service of some from our pilot scale recycling technologies and the pilot scale recycled fiber reprocessing lines, which generate much high value products. And of course, we can do life cycle analysis and cost modeling for particular industrial requirement and application. And we also do customized and tailored design, no matter that's product design or sustainable composites manufacturing system design. So we're also coupling with digital twins to make sure all our recycling and reuse process are digitalized and visually and easily used. And we also support feedback over data, support the policy and the legislation decision. So that's the visions for the sustainable composites. And what's the calibration status? We already secured the engagement with lots of industrial partners, including the waste management and of course composites manufacturers and the material supplier. And because we generate lots of new data and lots of software development like design tools and companies also interested in this program. And what we can offer, we can tailor the materials and trial your ideas with our machines and do the material validations and the coupon testings for the mechanical behaviors, and of course design and manufacturing and prototyping and support industrial partners to do the market research and make strong business case and explore wider market for the sustainable material. Hope you enjoy the presentation and you interested in like approaching to the circular economy together with LMC. Thank you. So any questions?
Thank you, Jill, for that. So just in summary, I mean, I hope you've seen today that we've got a number of programs underway. There's a real kind of breadth of capabilities and technologies that we're bringing to bear to try and have some really tangible activity around net zero and being able to hopefully resonate with some of your kind of either academic or industrial challenges. So thank you very much for your time today, and we're really happy to take any questions that's through. So I think Alex, you've been collating some of those for us.
Yeah, so we've got a couple of questions so far. The first is from Susanna, who asks, why will it take 2 years to develop a digital twin? That'll be in reference to the Reconfigurable Pilot Line project, so I will take that question. I think that's a really good question, first of all. I think it has a number of answers. First of all, I think that even for the proof of concept cell that we're going to be producing and we're currently building, it has a number of quite complex moving parts. And in order to fully replicate all the behaviors that we're looking at, so robotic motion, manipulation of deformable material, laying down of fibers, in order to do that all accurately and producing kind of data that we can look at and trust, I think that is going to take some time. It's going to take, we're working closely with campus as well, who have a lot of expertise in this area, and we don't want to rush that. Second of all, I think that's just for the first cell, but when we do expand to multiple cells, those will have different manufacturing capabilities on them. And that means that we'll be dealing with a number of bespoke sort of digital twinning challenges, depending on whichever manufacturing capability is installed on each of those cells. And I think that another thing is that we're not just looking to kind of digital twin these cells that we've installed and that's it, game over. We're looking to actually develop a system for digital twinning that we can kind of provide to the market, something that we are confident can be used in a general fashion and can be used for digital twinning of these cells. You know, if it kind of goes hand in hand with the reconfigurability of the cells themselves, is being able to then install your chosen manufacturing capability on one of them and produce a digital twin using a standard method that we've provided. So there's quite a lot of work that goes into that, and there's also kind of the quality assurances that we need to sort of pass the test with industry as well. So we've got a lot of quite a sort of high bar for that. We've already started this process, though. We're already engaging with the market quite closely, and we're working on with possible future partners on a one-to-one basis to kind of develop these systems and see what their needs are so far. But hopefully that answers your question on that one.
Can I just add to that? I think it's important that just to say that there's a digital backbone that's going with all of this, and it's not just related to composites manufacturers. So what we're trying to do is provide a product so it's a kind of plug and play system for yourself. So and plug and play is very easy to say, but it's quite difficult to do in real terms, such that you can rely on that as as your business. So we're very much at the start of that process, and we're very keen to engage with companies at this stage. We don't have to wait till 2 years have expired until we can offer this service. So if you do have some needs, if it does resonate with you, please get in touch, and we can start that engagement.
Just to add to something Iain said there as well, which was that it's not just specific to composites. It absolutely isn't. It's very much that adds to the challenge of developing the system. Is it's supposed to be very general, and from a digital twinning perspective, that adds a layer of complexity, because when you're trying to do that, develop a method for doing that generally, as opposed to for one production process and one type of material, for example, it makes it a bit more complicated. But I've got another question here, which I think would be for Saira, which is how long do you think we might see it might take for novel fibers such as the ones you're looking to develop in more widespread production, so actually on sort of commercially available?
So initially we're looking at the lab scale production. So hopefully later this year we would have the lab scale production line set up, and then next year would be all about producing the fibers at lab scale and optimizing the properties. And once we've achieved that, then the next stage would be to scale up the production to pilot scale. And that's when we could potentially produce larger composite components, which can then be potentially used in commercial applications. So it could be maybe 2-3 years down the line once we get to that stage.
Yeah, there's a process of screening different polymer chemistries and surface treatments as well. So we should be able to get to kind of coupon level testing by the end of the year. So we should be able to kind of produce enough fiber in sufficient quantities to be able to manufacture physical coupons until then go through that whole screening process, so we can start to develop fiber product.
Okay. I think we've got a quite similar question about recycling, which is how feasible is it to have an entire product manufactured from recycled material, and how long in the future might that be?
I think personally, I have already worked in recycling. I reuse some nearly 10 years already. So that's already some new products are good enough in the market. But what we're gonna do in say is like we tailor the materials and also the reprocessing lines with our knowledge and skills, and try to generate much high value product. And the problem now is like if even you have the capable products, but lots of manufacturers and designers, they don't know how to use that all properly, and what is energy cost, or what is the mechanical. So there's no summary and no clear guideline for this. So to say like we at the same time not just developing the material and do mechanical testing, we also summarize that and generate a guideline for the industry partners. Actually, you can truly engage with us, engage with this material for like doing sustainable manufacturing for your future products.
Yeah, and just to add to that, I think the University of Strathclyde has already taken a wind turbine blade and effectively an end-of-life wind turbine blade, a small-scale one, and gone through the process of deconstructing it, shredding it, and reassembling the material into a new wind turbine blade. So we are actually, we can demonstrate that has already been done. I think what Jill was talking about quite eloquently in her presentation is about when it's appropriate to do that. Looking at the economic costs and the full kind of life cycle costs of being able to do that and make informed decisions as to what fibre to employ in what location at what time. So that's part of the portfolio of skills and technologies we hope to bring.
Okay, well, that's we've got to the end of our list of questions now. Our contact details are on this slide. Please do get in contact if you have any interest in the projects and the work that we've described. We'd love to hear from you. But I'm going to just pass on to Iain to round off the presentation. You're on mute, Iain.
Sorry, we've just had one other question from Brendan. So what is the benefit of concentrating on SMEs rather than big industry players? I think it's the answer to that is SMEs are very pertinent to the discouraged context, particularly within composites. But by no means are we excluding larger companies from this. And indeed, we do have plans to use the reconfigurable pilot line cells to have a presence in larger companies. So it would be really helpful for us to be able to develop a technology within a large company and refine it just at a cell level, and then perhaps bring it into the RPL system within LMC and MaaS to be able to kind of demonstrate how that technology is scalable. So large companies are very much part of our strategy as well. So we're by no means excluding them, although today we've probably focused on SMEs because of the context.
I would just add to that as well that the current sort of landscape in Scotland is a prevalence of SMEs. So it's absolutely not about excluding the big players. We need them. We need everyone for the ecosystem to work. But it's about catering to the SMEs, and when there is a risk of shutting them out, I think if you develop expensive systems, it puts up barriers. And I think that what we're trying to do is to ensure that from the start, those barriers don't exist. And we've had really good engagement with technology providers as well, because they see this as a potential gateway into industries for their product. So if we can provide something, and it's really challenging to do, to make something economically viable at the scale. So hopefully the lessons learned in doing that will be translatable to larger industry as well. So we really see this as a great opportunity to build something quite unique and important. We're just getting some more questions. Just to Jill, sorry, you've already seen it. I think it's just talking about GFRPs in cement production.
So I saw one of our attendees very interested in glass fiber recycling. So of course there are so many like technologies you can do the end of life glass fiber waste. The things like most of them are do downcycling, which is related to like mechanical recycling. Basically, you just shred it, and the fiber properties after recycling is not good, and you can't. There's no point. You can't even compare like 10% of the virgin fibers. What we're gonna do in Strathclyde actually not gonna do is already being done. Like we can recover like at least 80% of the properties of compared to the virgin glass fibers. And what is the format of the what is that in application, the life phase? So after the recycling technologies, like glass fiber is similar to the carbon fiber. It is like a discontinued format and a random fluffy. So we can either make it into chop strand mat, which is like widely used like construction material, or with our LMC, like more advanced technologies, we can make it commingled with carbon and other any materials based on what application it is and what performance required, and make it much valuable even compared to like a traditional virgin glass fiber products. So hope that's answered the question.
Yeah, and again, there are just some, there are a lot of thermal and CO2 challenges with cement, and obviously glass reinforced cement could potentially, they could work together in terms of kind of recycling and reclaiming and that kind of thermal equation that would go to kind of balance some of the challenges. So yeah, I think we need to take a kind of holistic view to that as well, and see how we can combine both of those technologies to better effect.
Okay, so thank you for those questions, for all the interesting questions that you've asked. If anyone has any final questions, I'd just like to ask, just before we bring this to a close, just to make sure no one.
Yep.
I think on that then I'll pass over to Iain to kind of close off the presentation. Yeah,
no, just briefly, thank you again for taking the time to join us today. Thanks to my colleagues for presenting, and hope you enjoyed the session and found it useful. And I'll now hand over to my colleague Deborah Sherry to close the session. Thank you.
Thanks very much, Iain. Thank you. And just to reiterate what Iain said, thanks very much for taking the time to join us today, and to all our speakers from the Lightweight Manufacturing Centre. Shortly after this session, you will receive a survey, and we'd be really grateful if you could take a few moments to complete this. All your feedback does help us shape future webinars. We have one next week, an MaaS Insights on Wednesday, the 12th of May, which is all about our Manufacturing Skills Academy. You'll find details of this and all our future webinars on our website at nmas.scot. And I'm just going to now bring the webinar to a close. Thanks again for joining us.
Thank you.
Thanks.